resistor is, you know what a battery is, you're familiar with that kind of stuff. So a lot of the beginning stuff, you're not going to need to know. But I'm going to start going first through the first chapter and go through some basics. If you understand it, good for you. But if you have any questions, I want you to make sure you ask. So, and the way I'm going to do this is a little different than the layout in the book. I'm going to start with the most common circuit elements and talk about a basic understanding. Everybody ready? So here we go, day one. First thing we talk about is resistors. Resistor looks like just a jagged line. A few markers would be great. It looks like that. A resistor is something that limits current flow. Now, you got a lot of mechanical engineers here. You know the pipe's diameter limits the ability of water to flow through a pipe for a given pressure. That's the best analogy I can come to about this. So a resistor is something that limits current. It looks like this. It's just a jagged line. How many remember that from physics? Probably a good. Next thing we talk about, the next element is a battery. Now a battery can have several symbols. This is called a simple 9-volt battery, something like that. It just has a symbol of a large plate, a small plate, plus to minus. Then there'll be a voltage rating here, V. You commonly see 12 volts, 1.5 volts. Your car battery is 12 volts, a little higher than that. But you know what a battery looks like, right? How many do? All right. The battery is a very common thing you see all the time. And what it really is electrical pressure. If you think, since we got a lot of mechanicals, but other people know this, when you have pressure between 2 points in a piping system, nothing flows unless there's a way for the pressure from one point in the piping, like the pump, to get to the other. And that would be what the resistor will allow. You all with me? So this is like an electrical pressure of voltage. These are called DC voltages. It means they don't change with time. We'll get to AC voltages and they change with time. You all follow me on this class? This is a DC voltage, the most simple. So this is an electrical pressure. This is something that resistance. Now we say that if you have a voltage, and when I say voltage, I'm gonna throw some things in that I think you know. What is actually happening is this wants to push current, the symbol is I, around this loop. Just like water would flow in a pipe, if it could. You all with me? And then there's something, a very simple law, it's called Ohm's law. And Ohm's law says that current I is equal to the voltage or the pressure divided by the resistance. That's it. How many remember that? The most common thing you're going to see in basic circuits. When I was in high school, I had electronics. I remember that was the first thing we learned, and it was very simple. So the obvious thing is, if you want more current, you would decrease the resistance. Or if you can't change the resistance and you want more current, you simply increase the voltage. I think we're all clear on that. Can you, in the back of the room, can you guys see us okay? All right, now yell at me if there's something wrong. Don't worry. I appreciate comments because a lot of times I can't tell if I'm getting through to you or not. But if I am, you don't have to say anything. If I'm not, let me know. And a lot of times my handwriting is anything but good. I'm trying to get this. I thought I had all the lights on. We got some burned out lights here. You guys, you have enough lighting, right? I think you're fine. All right, so with that lights out, we're going to change it. That's the basic thing. Now you've seen that, right? Something that's implied here is if you have any device, and this is, I'm going to just take this, any device at all, it doesn't matter what it is, but there's a voltage difference plus to minus across those 2 points. Now, just think of this. How many of you use the voltmeter in any application at all? You know that normally you have something called a negative or ground terminal. That's the terminal where all voltages are measured with respect to. Then you have the positive terminal you put on another point in the circuit, and if it's a positive voltage, it means that current would like to flow from the positive to the negative point if possible. You all with me? So current generally will do that. However, now listen carefully. If positive current I enters the positive terminal, of a device, then it has to have a sense of polarity, like there's got to be plus, minus. You all with me? The power, and this is a standard thing, I didn't put the units here, but I might as well. Volts, V are volts. It's universal. R is the resistance, the units are ohms. The symbol is omega. And current, the units are amps, or amperes, really just amps. Now, with this, the next thing I'm going to mention, I'm trying to do this all at once, because most of this is old hat to you. If you have positive current entering the positive terminal of a device, there's power. And it is equal to I times V, and the units of power are watts. Usually just W. You all remember that? It's all very basic. Now, resistors can't create power. But if you had a source, remember I didn't label this as a resistor, I just said it's something. You all with me, class? Now, if you have a voltage source, but I didn't say it's a source, and now I have plus to minus voltage, but the current is leaving the source. The way you always get power is you find the positive terminal of the voltage, which is on that element, and you take a look at the current. If it's going into the device, then the current we consider positive. If it's coming out, it's negative. Here, the power is equal to minus V times I. It would be a minus, which means it's being supplied. It's not dissipating. That's all it means. That's it. Y'all with me, class? There's nothing deep here. It's just a simple way of bookkeeping. Now, one other thing that always happens in circuits, and this is intelligence theorem, but really it's basic physics. It's conservation of power, conservation of energy. If you take the sum total of all the powers on the element shown in a circuit, it has to be zero. All the power that's supplied has to be dissipated. Y'all with me, everyone? And it's that simple. So this is the most simple, in my opinion, it's just something you already know. I'm just making sure you remember it, okay? How many so far with the stuff I've shown you remember this stuff? All right, if you don't, you need to be really attentive, because this is considered what you've already had at this point. This is just review. All right, now, especially with resistors, we get into what happens if they're connected different ways. And this is important. Some of you may have had trouble with this in physics. I don't know. I'm just guessing. All right. By the way, are you recording?
I am,
okay,
yes.
Good. And just give me an idea. Is that an iPhone what?
14.
Okay, now, as I understand, that's pretty high end. You're probably going to have no problem with that video quality. And I think that adjusts, it has an automatic gain control for lighting and stuff, which is remarkable. About 15 years ago, that would be a $2,000 piece of equipment, maybe more. This is the other thing that I'm... Hey, one other thing, if that Wi-Fi comes back on during this lecture, let me know. I mean, if it does, I'm not saying it's gonna, but there's a reason, because I want to make sure everybody can access the stuff I put up there, but I can't even access it now. All right, I need to get a better eraser for this. All right, let me continue now. All right, next thing we're going to talk about is how we deal with multiple resistors with a voltage source. You with me, class? All right, so I'm going to come up and I'm going to put a voltage source like this. And here I'm going to give you concrete values. I'm going to say this voltage is equal to 100 volts. All right? It's a DC voltage. Now I'm going to put a few resistors. I'm going to say I have a resistor here, and a resistor here, And I'm even going to show you something called the ground potential. All right, now I'm going to talk about this. The only thing I did is added another resistor, right? I'll say this resistor, call it R1, and I'll say that R1 is equal to 100 ohms, and I'll call this R2, and I'll let R2 equal 500 ohms, all right? Just for kicks. I haven't thought this one through. Just pulling numbers. All right? It's something about numbers make it a little more real to people. All right, now, after that, the question is, what's the current flowing there? Now, some of you know, don't answer, but I want you to just think about it. If you're asked for how much current is going to flow there, the logical question is, does the same current flow through both of these? The answer is, think of water in a pipe. You connect as many pipes as you want together, right? If it's an incompressible fluid, the same rate of water flow through one is the same through all of them. Y'all with me, class? That means the current is identical. And if the current is identical, they are in series. Do y'all hear me? So it wouldn't matter how many there are. And I'm going to show you this off to the side, but I'll get back to that problem. So if you have a resistor here, and another resistor here, remember the current has to be the same. Literally, if you could spray paint a piece of charge here, say an electron or whatever it is, and you watched it move, it'd go through one, but it has to go through the other. Y'all with me? There's no other option it has. And there could be another one. And this thing could go on until you had R to the nth of it. And you wanted to know how you could reduce the complexity into a single resistor. Y'all with me? Now don't answer how many know what to do. I bet you all of you do. Add them up. All those resistances just add. So the entire equivalent to that is a single resistor R that is simply the summation, I'll call it R total, of Ri, where I equals 1 to n. You just add them all up. You all with me? I'm saying it for a reason, but I'm going to actually get more information. You all with me so far? Very easy stuff. So for this particular example, I can say I can make the circuit right here equivalent to this. Put it up here. Now, I wish I had these. The physics department has these multiple boards. Have you ever had classes over there where they get like 3 or 4 boards and they can, oh man, that is nice. I'm going to put a bunch of formulas in one of these corners. I just wish I had a bigger board. All right, so what this circuit is equivalent to, if I'm just after the current, is this. I got a voltage here of 100 volts, and I have a single resistor. And by the way, it doesn't matter if the resistor is horizontal or vertical or at an angle. The only thing, and I didn't say this, the only thing this is some kind of conducting wire that has no resistance. Y'all with me? So it doesn't do anything to limit current. It just allows this point electrically to be connected to that point. Y'all with me, class? Y'all use copper wire, haven't you, in your circuits or your in physics or something? I mean, I shouldn't say, a lot of people have had to build things, you know, breadboard or fix things on their own, so they're familiar with this. All right, so this resistance is the sum of this. So that's going to be 600 ohms, right? So what's the current flowing here? I want that next. Anyone? 100 over 600, or 1/6, right? Of an amp. You want to play Jeopardy? We can. For $500. Yeah. So it's 1/6 of an amp. Everybody with me? Just 100 over 600. All right, now the next question is, what's the voltage across each one of these components? So we know the current, right, flowing is 1/6 of an amp. So now what's the voltage across this 100 ohm resistor right here? Think of Ohm's law. Ohm's law says either V is equal to IR, I is equal to V over R, right? Or R is equal to V over I for a given, they call it a bulk parameter, a lumped element. You all with me, class? So what is it? Well, it's 1/6 times what? 100. It's 100 over 6, correct, class? So this voltage here is just 100 over 6 volts. Y'all agree with that in the back? Can y'all hear me? Far back. All right, now what's the voltage on the other one? Yeah, and you're gonna, now we talk about something called Kirchhoff's voltage law. So this voltage right here, and the plus minus just indicates the polarity, is going to be 500 over 6. Or, yeah. Y'all with me, class? I don't need the exact value. I'm just going to leave it fractions. Y'all with me, everybody? Now, something that is implied, and I never said it is, well, if I sum the voltages around this closed loop, I have to start at a single point, and I want you to listen here. It's very important you hear me. This is where mistakes are made. So it's Kirchhoff's voltage law says the sum of the voltages around any closed loop will be 0. That's what it says. Let's see if it works. I'm going to start at this point. You always start at a point. Call it A. So I come, and notice I hit a negative to a positive sign of voltage. This is important. Now, pay attention. Y'all hear me? Anytime you go from a negative to a positive as you're summing voltages, that is a voltage increase that's considered positive. Y'all hear that? So it's going to be plus 100. Now, you see I hit this point, it goes from a positive to a negative. Y'all with me? That's a decrease. It reduced the amount of voltage. So it'd be minus 100 over 6. And then you keep going, and you're going to hit what? Class, can you all see it back there? Minus 100, or minus 500 over 6. Agreed? And y'all can see that that is 0. So that's called, and I'm just demonstrating it in a very simple way, that is Kirchhoff's voltage law. So if by chance I didn't know this voltage, but I knew these two voltages, I could always ascertain that one just by summing around the loop. Y'all with me? That's it. I'll go through examples. Now something else I want to talk about. I've talked about power, right? Remember, the sum of all the powers associated with the circuit have to be 0. Do y'all remember that, class? So just take a look at this. Let's start here at point A, right? Here, I have the positive here. Positive current is leaving the positive terminal, right? That means it's a negative. Y'all with me, class? So it would be minus 100. And then it's going to be times the actual current, 1/6. Now that, by the way, that will be the total power supplied in the circuit. Y'all see that? Doesn't matter how many other resistors are there, they can't supply power. So the amount of power supplied, if you will, is going to be really minus 100 over 6 watts of power. It's really you would never see a negative sign. What they would say in the real world is it would supply 100 over 6, right? Or 50 over 3, or you can break it down any way you want. Watts of power. Y'all with me, class? By the way, what's a hairdryer these days in power? Anybody know? Typically. 1,000 watts? 1,200 watts. Well, you got a high class on it. You don't have a hairdryer. Your girlfriend's hair. Anyway, hairdryer's about 1,000 watts, plus or minus maybe 50, or maybe 500 or 600 watts. That's actually a lot of power to put in a small unit. It gets pretty warm, right? Typically, the old incandescent lamps, I don't even think those are LED. You remember those 100-watt bulbs? Anybody? Most of the actual heat in the 100 watts for that bulb was actually just heating. It wasn't light. Y'all remember that? Then they went into fluorescent lights and now LED lights that have a much higher percentage of the power transfer goes to actually light, not heat. And y'all know that incandescent lights, I think they're not even sold anymore, are they? No folks? In the store. They are or not? I don't, and I understand the reason for it, but by the same token, there are certain applications, incandescent lights are better because they don't have that flicker. Those have a 120 hertz flicker, believe it or not, they tire your eyes out. From what I've been told, I'm not an optician, or an ophthalmologist, but that's what I've heard. All right, so I just mentioned that, that's the total power, but if you sum the powers around here, I think everybody can see it. You're going to get 0. Can you all follow me? All right, any questions so far? Now, the next thing we're going to do, these are called resistors in series, and it's a very simple example, but it showcases what I need you to see. I'm going to show you resistors in parallel, and I'm going to give you some circuits, and I like doing problems to showcase this. And I got plenty of time, but would you do me a favor? When I got about 5 to 10 minutes left, somebody mention it to me so I don't really overwhelm you. I'm notorious for running overtime, and I don't want to on the first day. By the way, is this the biggest class you've ever been in? 115 kids? Really? On physics or something bigger? This is the biggest class I've ever taught in my life. This number. I've never. I mean, I've had, I guess when I've done short courses, I had more people, but I mean, for an actual classroom that meets for 10, 15 weeks, this is a big one. All right, next we're going to do resistors that are in parallel. Now remember, with resistors in series, the hallmark is the same current goes through every single element, right? With resistors in parallel, it'll have the same voltage across it. Let me give you an example, and I'll show you how to do it. So, if you have a voltage here, V, and let me know if you can't see it, I'll draw it larger. And now I'm going to put a resistor here, R. I'll call it R1. I think by this time everybody can see that the current flowing through here, call it I1, would just be equal to V over R1. Does everybody agree with that? Now I'm going to add another resistor, but it's going to be what's called in parallel. It'll have the same voltage across it as this one. Here I'm going to call it R2, and I'll call this current I2. Can everybody see it has the same voltage? And some people may want to ask a question like, how do you know? Here's how you find the voltage across any 2 points. And I think when I had this, when I was in high school, what they did is say, the easiest way is to find find a red pencil and a blue pencil, or something like that. If you want to know what has the same voltage from a given source, say this battery, you take this and well, this ain't gonna work, is it? So basically, you're going to go from that point and you connect. This is like the curse I've always had with these markers. They are never the ones that just don't go bad. I think I have this blue one, but let me go this way. Let's see if this works. That's not even that. This is something else. Right. If you come here, and if you had a colored marker of some sort, and came down here, and you go everywhere you can before you hit an element, a resistor or something like that, or a source. You all with me? That entire thing that I just colored in has the same exact voltage across it. There's no difference. You all with me? Then you take a different color, typically. This one's going to be hard to erase. And you come up here from the top, you go like that. And everything between the black and the blue squibbly has the same voltage. You all with me, class? That's it. That's the simplest way to do it. It has the same electrical pressure. What would I2 be flowing down here, by the way? The voltage is V. The resistance is, can you read that? R2. It's supposed to be R2. So this is simply V over R2. You all with me? I'm going to add one more, and I'll make my point. So I'm going to add another resistor. Same voltage across. What's this current I3? It's not a trick question. I couldn't hear. Don't be afraid, just anybody. Help me out. Just V over R3, or whatever I wrote, right? And I can keep on going, be V over whatever that R is. Y'all with me? So here, it's going to be V over or really over R3. Now, where's all that current coming from? Here. The current here is equal to I1 plus I2 plus I3. Can everybody hear me okay? I'll wear a mic if I have to, but I hate wearing that thing. Everybody with me on this? That's it? Now we can do something that should make sense. I can say, well, I have this voltage source, right? And I want to get an equivalent resistance for all these parallel resistors. Can you all see that, class? So the definition of resistance is the voltage divided by the current in the element, right? So it's the voltage is V. Just watch, you'll see. And what's the current? Well, it's V over R1 plus V over R2 plus V over R3. And we could extend that to as many R's as there are in parallel. How many see that? Can you all see it back there or not? The logical extension is obvious, right? Just keep on putting 1 over R, right? What do you notice about the V? Cancels. So basically for this, just 3, it's just 1 over R1 plus 1 over R2 plus 1 over R3. As a matter of fact, you could add as many as you want to that. So really, I mean, I'm just showing you an obvious thing. If there was 4 of them, there would be 1 over R4, right? 5 of them, 1 over R5. You all with me? That's all there is to this. Now, I just gave you that, so I'm going to ask you this next. If this is R equivalent, so I can basically say all these resistors, if I was simply worried about an equivalent resistance that would represent their effect on that source voltage, it would be this, right? So, what happens to the actual, I mean, if you were asked this question now, use your logical abilities and don't answer it, just think. If these are 3 different value resistors, you all agree they have the same exact voltage across them, right? And I asked you which one of those consumed the most power. How would you determine that? Think about it just for a second. Well, power is voltage times current, right? So it would be the one with the most current or the one that had the least resistance. Does that make sense to everybody? As a matter of fact, the reason I mention that is I want to say something about how you actually determine power. Power, I said, was V times I in the most general sense. Right here we're talking about current going into the positive terminal of the device. You all with me, class? Well, but if we use Ohm's law and write this down, this is handy. You'll see it. Since I also know that voltage is really I times R, I can say this is really R times I squared, can't I? If voltage is I times R times I, it's I squared R. How many see that? Obviously, I squared means the power is proportional to the square of the current for a given resistance. But if I say that I is V over R, then I get V squared over R. Can you all see that? All those are identical in what they're telling you. Now, the reason I brought up this point about which one would consume the most power, they all have the same voltage. The only thing different is the resistance. And you can see if you wanted to make this term large, you would want to make R small. Y'all with me? In the limit, what happens is R goes to 0. Yeah, it looks like power goes to infinity, and it does if you can maintain that voltage, but the truth of the matter is you can't. The voltage will drop to 0 too. So don't worry about these kind of, everybody likes to look in the limit. Mathematicians love this. And in the real world, you can't get an infinite amount of power. Trust me, I know. But can everybody see the process that we're talking about right now? And everything we're doing here is just straightforward. It's meant to be simple. There's nothing tricky. I'm looking at his book. I'm very familiar with his books and circuit analysis, and I know, frankly, there's a lot of things you don't have to talk about. I mean, the concept of power by this time in your careers, you're all engineers, is pretty clear, You can think of it every which way you want, and energy, right? Power is really the use of energy per unit time, right? And the more power you're using, the more expensive it is. That's a good way to think about it. Okay, now, some of these problems are just silly, and I'm not gonna cause you a lot of grief with this. All right, now, next thing I'm going to talk about, actually the next thing, very simple thing is what I showed you a second ago, and that was a symbol that I didn't address. This is called the ground. How many are familiar with the term electrical ground in any application at all? I don't care if it's just you're in high school and you have to connect batteries. What I told you about earlier, the ground is the point that's considered zero potential, that everything is measured with respect to. But I do need to be clear about this, especially for mechanical and civil engineers. Are there any civil in here? Any at all? There are no civil engineers? They don't have to take. All right. Well, in mechanical engineering and other forms of engineering, I'm not sure about industrial, and there's probably other ones I'm really not sure. When you talk about doing work where you have a license, like you're a professional contractor, I have an FCC Class 2 license. I don't have the Morse code license, but you're liable for stuff. It means you can get sued, and at times you can go to jail if you're not careful. So there's things you become liable for. Now, an electrical earth ground, have you heard that? Anybody else heard of an earth ground or an earth grounding rod in here? That is a thing that you're supposed to drive into the ground. It's a solid piece of copper steel thing with a certain diameter, a certain distance in there, and when it's measured between that point and the resistance between that point and another point, and I forgot how far away the second grounds are, it has to be below a certain thing for it to be considered a true electrical ground. It's very important for lightning protection, and legally speaking, if somebody does work, it's a general contractor, doesn't do that right, and your house burns down because it gets struck by lightning and somebody else, they can go after that guy. He can get a lot of trouble, he can lose his license, and get sued, so the nth degree. Anyway, that is considered an earth ground. Now, some of this when I'm showing you here, this like 3-line thing with progressively shorter lines, that's really called a chassis ground. And then there's something called a signal ground. I'm not going to differentiate that. Anytime you see this symbol or this symbol, they will appear like this. One of them's chassis, one of them's chassis, the other is signal ground. Don't worry about it. They're the same to you. All right? There's no problem there. But if you see this symbol, that is an earth ground. And that is one thing you have to be, if you see that in a schematic diagram, if you're working as a mechanical engineer or something outside. Any arrows in here? I don't know about aerospace anymore because you do have things that are tethered to the ground, and you will need grounding rods to certain things. But that is something that requires, you have to be very careful about this, and you have to know what the laws are in the state you're at. It has to be done exactly right. That is not a connection to a zero voltage. I mean, you can't connect this to house wiring is neutral. You got me on this one? I'm just making it clear, so, because I had students, God, I've had somebody, unbelievable. Has anybody heard of Rocket City Rednecks? Are you from Huntsville? Do you know Travis? Okay, he was one of my students. Travis loved mischief. As a matter of fact, he could find ways of causing mayhem. And he somehow got a job to create this, I forgot some of the videos. He had like some kind of a rocket that would like lift off a small animal up there and parachute it. But you know, this is the kind of stuff. You tell him, you never want to do this. He didn't do this. Don't anybody do this. I don't want to get sued. But you know, railroad crossings are just two long electrical lines, right? He was in my class. And if you happen to take a voltage source, like a car battery, and put it between the two and tap it, an electrical signal goes down the line. And that electrical signal can do something with a crossing gate. And it can also do something with switching. Now, I don't know what the parameters are for this, so hopefully it's changed. But Travis would be the kid who, really, I don't believe it. And he'll go out there. It's extremely illegal to do stuff like that. Not a little illegal, like you go to jail big time for stuff like this. FCC laws, transport laws, these are things, they don't smile at you and the judge says, oh, well, you've been naughty. No, you go to jail. I mean, real jail. It's mandatory. I forgot how many years you get for like an FCC class 1 violation. I thought, wasn't that bad, but you do that, you go to jail for 5 years and you can't do anything. If you're found guilty, it's over. So be careful about certain laws. And some of you, especially people that build things that are mechanical engineers, you gotta make sure what you're liable for. And I'm telling you this because I know what I'm liable for and I won't do it. I just will not do anything where I can go to jail anymore. I'm not gonna do it. Anyway, it's not illegal, it's just, for whatever reason, if something breaks, you're going to court. So that's another side of the story. Anyway, if you get a chance, look at Rocket City Rednecks. You'll know what I'm talking about with this guy. He finds a way to make things disastrous. Anyway, back to this stuff now for the last part of it. We're talking about an actual type of circuit analysis where we're going to cover all the bases. And I'm going to just tell you right now in a short form, some of you already see this. I told you Kirchhoff's voltage law, where the sum of the voltages around any closed loop was 0. Kirchhoff's current law is similar. And I don't need to write a lot of elaborate math down about this, but it's very simple. By the way, in mechanical engineering, do you have that project anymore where you have to build like a pneumatic cannon, or don't you?
They changed it, I think.
They probably changed everything. They changed a lot of my labs too. I mean, we used to have fun, but anyway. Now, remember I told you about Kirchhoff's voltage law. Some of the voltages around any closed loop is 0, right? Well, Kirchhoff's current law is the same thing. Let me show you. If you have a junction, like so, this electrically means that all these things are tethered together. They have the same voltage. You with me? But if you have a current going in, and this point where they can come in or out of is called a node. You hear me on this, class? That's all it's called. And you have a current I1 there, and you have a current I2 there, and you have a current I3 there, and a current I4 there. Now it looks like you got a whole bunch of currents all going into the same point. And if they were positive, it wouldn't make sense. The bottom line is with Kirchhoff's current law, it says whatever goes in must come out. When the sum of the currents entering a node, and the symbol is just N, sum of the currents entering a node is equal to 0. So if you summed up I1, I2, I3, and I4, it equals 0. The implication is if some are positive, some are negative. You all with me, class? Now here's the next step. If I1 was 5 amps, and I2 was 5 amps, and I3 was 5 amps. Remember, the direction of current is assumed positive. You all with me, class? That means that I4 has to be minus 15 amps. You all with me? Whatever goes into it comes out of it. It doesn't accumulate. You all with me, class? And that's common sense to a lot of you. But there are some subtleties. You can have pressure buildup, and you can have basically some sort of increased size at a juncture or a joint in piping with compressible fluid. So it doesn't always matter or hold true, but it holds true almost always in electrical circuits. There would be another device shown there that would allow you to accumulate charge, you might say, and that's called a capacitor. But don't worry about that right now. I just want you to know that. Now that's the basics. Are there any questions before I get to my next point? Now in the back, have you been okay with the board? Guys, you can hear me all right? All right? And you can see it. I'll get something to erase it. So I just want to make absolutely sure. Is our Wi-Fi back yet? Anybody? It is? Could you guys please, if you have access to it, go to the link I sent you. If you can get to your email, go to the link I sent you and make sure you can access the Canvas page. It should have a syllabus. Anybody confirm that from this classroom, not from yesterday? You can? All right. Anybody else?
I don't have Wi-Fi.
I don't either.
You don't have Wi-Fi?
Mm-mm.
This is usually the problem in my life here in a class this size. Some people have it, some people don't as far as access, and that's troubling. Because I don't know what's wrong. Huh? Say it? What?
The Wi-Fi's been in and out the last 15 minutes.
Oh, it's intermittent? Well, they're working on it. God help them. What? All right, I got a minute yet. All right, so here, we're going to do one quick thing, and you guys are going to be out of here. Write this down. This is on page 29 in the book. By the way, would you do one last thing I got to tell you? Because I'm going to be asked about this. Could you please see if you can get these books by next class period? If you have gone to the bookstore, and by the way, there's probably used ones out there. I don't know. If you want to order it online, fine. I don't care. But see if they are out. If you cannot access a book from one of these bookstores in the area, yeah.
Since we can't access Window, what is the title of that book?
It's on the syllabus, isn't it? Didn't I post this thing that I took a picture of it? It's called Essential Electrical and Computer Engineering. It's by J. David Irwin and Kearns. But I literally posted a picture. Does anybody remember that, seeing that? You saw it? I posted a picture of this thing so you can't mess up. And I have stories about kids ordering the book, and they looked at the ISBN number, and they had somehow changed one or two characters, and they get the wrong book. It's hard to mess that up. Anyway, let's do this real quick and see what happens here. This is on page 28 of the book. Am I out of time? Well, maybe I don't have time for it. We'll do this next time. Now look, I'm going to give you some homework. It will be on Canvas. I'm sorry, on OneNote. And I will, well, yes, sir.
I know that I can't access the Canvas page for this class, and I don't think I'm the only one with this problem. And likewise, I have.
Why can't you though?
I don't know.
Did you get the link?
I have not received any emails in regards to this class.
Hold on for 1 second. Has anybody, who has not received an email after they looked for this class on Canvas? If you have not, would you please come down right after class? I want to rectify this ASAP because honestly, I'm sending out the email. If you just added the class,